Hello viewers, welcome to Timas TV. Today we are looking at transmission line, and on the special note we are looking at long transmission line. That is long transmission line, um, mission line in electrical power system. And actually when it is long, it means that the line is from 240 kilometers and above, and we'll pay special attention to some of the parameters. We'll look at Z that will represent series impedance. We'll also look at Y. Y is representing shunt admittance. We'll look at L. L is the actual length of the line. And we also express ZC is actually a square root of Z divided by Y, and that is what we call characteristic impedance. Characteristic impedance. I'm going to use gamma to represent, that is square root of Z and Y, and this is representing propagation constants of the wavy line, where we can also express as alpha plus beta, and where your alpha is iteration constant, and beta is the first current. And we are actually considering R to be the resistance. L is actually inductance, and C is capacitance. So let's first of all represent the root mean square voltage and current of the line, where the first anchor at a particular location the line is represented. So we have that the root mean square of voltage of that line is always actually equals to this. The root mean square value of the particular line, that is the root mean square voltage, is always given as 1 divided by 2 VR. VR is the voltage of the output terminal plus IR ZC, and IR is the current of the output terminals. This is exponential this plus, and we have VR minus IR ZC multiply all by this. So this can be used as our equation 1. And also let's look at the root mean square value of current. The same thing, 1 divided by 2 1 divided by 2 VR divided by Z, that is characteristic impedance, plus IR, multiply this by this, minus 1 divided by 2 in IR ZI minus this, or multiply with exponential minus xy. Now, but to reduce equation 1 and 2, we can actually use this trig identity, say sin theta is always equal. So that is a relationship between this and the exponential function, exponential this minus exponential this, and also cot theta is always equal to half exponential theta plus minus exponential minus theta. So we are going to be using this equation 3 and equation 4 to actually reduce the complexity of equation 1 and 2. So at this point, we can further, based on equation 3 and 4, we can actually write the root mean square equation as V equals to VR cot this plus Z sin, and so it is x, y, x. That is equation 5. Also have this, and that is the root mean square value as IR cot yx plus VR ZA sin this. That is giving us equation 6. So at this point, we can say that at the descending end, please take note at descending end, x is always equal to L, that is the length. So we can represent equation 5 and 6 as ascending end voltage Vs as VR cot YL plus YL. For the current semi-end current, we have this cot YL plus VR ZC sin YL. So we can actually make something subject of the formula. So let's see what we can. So at this point, in order to further simplify the equation, we can try to make VR and IR subject of the formula. So at this point, we from equation, let's call this equation 7, and we can call this equation 8. So we can from there say we can from here make this, so we can actually say that VR coach YL is equals to this minus coach YL. So at this point, we're dividing through by coach YL. You can have V is coach YL and coach and sine YL we divide by coach YL. So that is it. We also write out for the sending current, which is this coach YL plus sine this. So the replacing V, we can actually have coach YL plus using this in place of VR. So we can have this V divided by coach this minus Z divided by coach YL. All this multiplied by sine YL divided by ZC. So we can actually further reduce the expression by multiplying through by this, multiplying this through by this, and that will give us IR coach this plus VS divided by coach this minus ZC divided by coach YL. So sine this divided by, so we actually realize that the current, sending current, you can have coach YL plus VS sine YL divided by ZC coach that minus IR sine squared divided by coach YL. You can see that this is multiplied with this and we have squared here, and also ZC cancelling out ZC, and we don't have that here anymore. So further reducing the complexity of the equation, we can factorize this out using this and this. So that will give us coach squared YL coach YL minus sine squared YL divided by coach YL. So that is it. The remaining part of the equation is VA sine YL divided by ZE cot YL. So having done that, we realize that IS, when you factorize this and this, you're having this and you're left with this. So in order to further simplify the equation, we can have the LCM at this point. So let's see how we can further with the LCM. We are having that in IS, we're having that IS is equals to IR into cos squared minus sine squared YL all divided by cot Y. In brackets, we have VS sine YL divided by ZC cot and YL. So at this point, we can also um, apply this identity that says that cot squared theta minus sine squared theta is equal to 1. So at this point, the whole of this, we can call it b equals to 1. And we can call that the whole of this will be equals to 1. And because of that, we can write this way, that this is going to be so having this identity we can apply in this expression. So we're going to have that IS is going to be IR divided by cot YL plus VA sine YL divided by cot YL. So we can multiply through by cot YL, and that will give us S. Having provided this, so the whole of this is 1. That is why we're having current times 1. We have this, and this we have this. So we can multiply through by cot YL. So this is going to be cot YL is equals to plus VS divided by C. This will mean we have that. So at this point, we can say that your IR is equals to VS. VS IR is equal to VS, that is minus VS sine YL plus IH cut YL, or you can write it preferably like IH cut minus VH divided by this sine YL. We can call this question. So having done so, we can provide the same information, put it in VR, and VR is actually equal to V is divided by cut YL minus IR ZC sine divided by cut YL. So when we introduced this equation in this expression, we are having that VR is going to be VS divided by cut this minus we have Z sine divided by cut YL, introduce IL into it, have cut YL minus VAZ this sine Y. So at this point we have this further written as VS divided by cut YL plus sine squared YL divided by cut YL minus Z this. So this is the result when we actually multiplied. This is this. So when we multiply this and this, we have this. And also when we multiply this into this will cancel this out. And this will multiply this, we have squared. And this should going to remain. So we can further improve, reduce the complexity by doing this factorize out, and we will have 1 divided by cut YL, and also sine squared YL divided by cut YL into, you subtract with this and sine YL. So when we are taking the LCM at this point, you realize that we are having that VR is actually this. So this is 1 plus sine squared YL divided by cot YL. This is giving us this expression. So at this point, we can introduce cot at this point, cot square at this point, and when we recall this identity that we had. So at this point, we can have that VR is equals to VR equals to VS divided by cot YL, we multiply by cos square YL, that is from here, and we subtract it with the sin YL. So that is how it is. We are on the road of simplifying this equation. So please you take the steps one after the other so that we'll actually you actually realize what we have got at the end of the day. So at this point we are having that V is going to be this, we'll cancel one of these and we are left with that. So it's going to be VS cot this minus ZC SR and YL. And this also you can recall is actually this cot minus VSZC sin. So this is the actual um, terminal voltage terminal value of the line, and this one is the value of the terminal output, that is the current of that particular line. So we are trying to see how the value of the terminal value that we would have at the output at the end of the relating sending parameters and the actual parameters of the line. So when we compare this with the medium line, this is for long line. So you can recall in our previous video that the terminal voltage, output voltage for medium is always this D minus B IS. We have this minus C minus AIS. So this is for medium line. So when we are comparing this, we realize that for a long transition line, that A is actually called YL, and whereas B is ZC sin YL. Please note also that C is sin YL divided by characteristics impedance, and also D is the same thing as A, which is this. But we should note that A is equals to open circuit reverse voltage transfer ratio, open voltage, open circuit reverse voltage transfer ratio. This is no unit, and B is short circuit reverse transfer impedance, short circuit reverse transfer impedance, short circuit reverse transfer impedance, and we have the unit is in ohms. We also have C. C is open circuit reverse transfer admittance. Open circuit reverse transfer admittance. And finally D is short circuit reverse reverse current transfer ratio. And this one we don't have, there's no unit. So this is how the transmission line is analyzed when it is long, and other is how the parameters of the line are related with the output values, that is VR and VA. Yeah, I haven't watched that analysis. I want my viewers to attend to this question and write the answers in the comment section. We are looking at this question assignment: determine the line voltage at the sending end of the single circuit 50 Hz transmission line, and with the following parameter. The length is 300 kilometers and the load is 127 megawatts at 220 kilovolts. This is the resistance. This is inductance and capacitance. This is 0. So I want you guys to write the answer in the comment section. Subscribe, share, and like. And also you can drop your comments in the comment section. I will always be online to attend to questions. Thank you very much, and see you again in the next video.